This is a introduction to the Module 6 acid and base topic, and it's just kind of an overview. So no one thing in here is necessary for your learning. It's just to kind of wrap your head around it straight away. Um, First thing I'd like to point out is obviously everyone knows water is H2O, and so ratio is 2 to 1. Acids are chemicals that donate hydrogens. That's the strict definition, and what I would like to loosen that up and just say acids are things that bump up the ratio of hydrogen in water. If you've got extra hydrogens or little protons floating around, that's going to make the solution more reactive. Bases are the opposite. They're chemicals that accept hydrogens by definition, but they're just chemicals that bring down the ratio of hydrogens to oxygens. And so the most common one there is OH, which is a 1-to-1 ratio, the hydroxide ion. A solution that does not have many hydrogens and has a lot of OHs is also reactive. And so what I'm saying here is the reason why this is a whole topic is we need to, as scientists, as living things, monitor the chemicals in the water, the pH of the water, what kind of ratio is in the water, I should say. I shouldn't introduce pH just yet. And the reason is that all life has chemicals in water. So you got your blood, you got your ocean, you got the water and soil, water and plants. Everywhere that there's living things, they rely on water, and the chemicals that are in this water, they need to. They're all have a structure, a certain shape, and that shape gives them a function. So your cells, your cell membranes and everything in it, but typically the membrane on the outside, even though there's water on the inside. Your proteins, that's your enzymes, so all the things that help, like the little machines of your body, they all have a certain shape. And if you have, if we just focus on the cell membrane and you have your cell membrane in an excessive hydrogen solution, then that excessive hydrogen might react with the cell membrane, cause it to change shape, kind of compromise it on the outside of it, and all its cell contents can just spill out. And same effect if we put cell membrane in a solution that's very basic, the hydrogens that are on the cell membrane might be plucked off by the OH in the solution, like the reactive solution, and therefore, because they've lost their hydrogens, they also change shape and might also lose function. And every chemical kind of gains and loses hydrogens at different levels. So you want to be able to monitor it. For the biologists in here, when you come across, and I don't know if you have or not, when you come across the terminology of denaturing proteins, this is the more concrete wording towards that naming. So you might talk about temperature and pH denaturing proteins. I'm basically saying that in a different way, FYI. So for acids, they're just things that bump up the ratio of hydrogen to oxygen, and they can be classed as strong or weak. Strong is something that fully donates their hydrogens. That doesn't mean it fully donates all their hydrogens. It just means one of their hydrogens must 100% break all its bonds. So if I had 100 particles of hydrochloric acid, all 100 of them would dissociate, split apart, or we could also call that ionize, which means they turn into ions. Okay. This is sulfuric acid. Note that I've only got the first ionization level here, so the first hydrogen being knocked off. The first ionization is a strong acid. That means it's 100% reaction happens, and we use a straight arrow for that. Note that if the second hydrogen were to break off and also contribute extra hydrogens, by the way, this extra hydrogen molecule, if you haven't come across it, it's kind of the centerpiece of this topic. It's the hydronium ion. I would say this is really what the acid is. Acid is something that contributes to this. This is the real problem, so to say. If I put my hand theoretically in a solution that was highest concentration of hydrochloric acid and there was no water present, I would not be at risk because this hasn't had the ability to split from the chlorine via this water particle. And so it's not an acid, it's not acting as an acid yet because it hasn't had the chance to. It can act as an acid if there's any water present, like say on my skin, but it's not an acid yet. It has the ability to act as an acid. And so this second ionization we'll be talking about a bit more. This is the hydrogen sulfide ion bumping into water and making the sulfide ion and another hydronium ion. And you'll notice that I have a Ka associated with it. If you remember from Mod 5, high Kas mean a lot of products and low Kas mean a lot of reactants. This is not the smallest. It's saying we're sort of favoring the reactants. So we've sort of got a bit more of these, although there is quite a considerable amount. So I'm not going to throw a number at it, but we're saying we've got slightly more reactants and slightly less products. The last strong acid that you need to know is nitric acid. And when it bumps, it makes a nitrate ion, which is always soluble. That kind of stuff might start to click with you. This is a very stable compound. There's reasons for that. There's a word called resonance that's outside the course, but there's a reason why this is a very stable molecule and is happy to hold on to the charge and not share it with a hydrogen. And it also is 100% dissociation. Where you start getting your more funky questions that start incorporating your Mod 5 understanding, because this is very much an overlap module. Weak acids, by definition, are less than 100% of their hydrogens for a particular hydrogen get broken, so it could even be up to 99.9%. By definition, if it's not 100%, if it's not fully, then we don't call it a strong acid. So we've got a huge range here. Weak acids can therefore be really, 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 really weak, or they can be relatively strong, but not by definition strong. And so here's some examples. This is the acetic acid or ethanoic acid, whatever you're more comfortable with at this point. This is the ammonium ion, and this is the 3 ionization levels of the phosphoric acid. This is dihydrogen phosphate and hydrogen phosphate. And you'll notice if I just go straight to, I'll explain them all actually. Remember from Mod 5 that Ka is very much temperature dependent. That's the one that changes all the underlying constants. And so at a certain temperature where all the underlying constants are kept the same, this is telling you that you'll have quite a few reactants. This is because it gets lower. This is telling you you've got a lot of reactants. This is telling you you've got slightly more reactants. This is telling you you've got a lot of reactants. This is telling you you've got a heap of reactants. Okay, so the more negative, the more reactants. And obviously what that means is a lot of them are staying with their hydrogens attached and not splitting apart. So if I was to make up numbers for this one, we could say out of 100 particles, only 16 split. So I'd get 16 acetate ions and 16 hydronium ions, and therefore there would be 94 that would remain. 16, sorry, good maths. 84 particles would remain in this state with the hydrogen still attached. And so what I would say here is I'd look at these numbers and I'd go, well, this Ka value, this equilibrium constant for acids, is the highest of the 5 written. So I'd say this hydrogen ionizes the best. This hydrogen ionizes the best. This is the strongest acid. It is not a strong acid. It is the strongest acid in this category. It also, something to point out is you'll notice that the first ionization is fairly, happens to a fairly high degree. The second one happens to a fairly low degree. And the third one happens to a ridiculously low degree. And I just realized I should probably be saying 1, 2, and 3. Okay, and that kind of tells me that it's the first ionization for this acid, the second ionization for this acid, and the third. And strong bases aren't too dissimilar There's a lot of similarities, but there is some subtleties. So strong bases, so anything that fully dissociates and they produce OH, okay? They might contain OH already, and that makes it really easy. And so any soluble hydroxide will by definition be a strong base. So for instance, sodium hydroxide, lithium hydroxide, ammonium hydroxide, think about your solubility rules, potassium hydroxide, all of them, because they fully dissolve and they give a strong, strong, strong contribution to hydroxide, in this case, all their contribution to hydroxide, they are strong acids. Now, magnesium hydroxide contains OH and so would be a strong acid if it fully dissolved. However, it's got a KSP associated with it, and so only a small proportion of it would be in the hydroxide form, and a lot of it will be wrapped up in the solid form. So magnesium hydroxide would not be a strong base, but it has the ability to if it dissolves. And that's for the solubility side of it, but you can also just have chemicals that partially accept hydrogen back, or partially dissociate or ionize, with those words being semi-interchangeable. Ionize means they turn into ions, and dissociate means they split apart. And I purposely chose what are called the conjugates. So you'll see up here, I wrote ethanoic acid acting as an acid. What that means is it's bumping into water, and it's donating a hydrogen to water. So it's acting as an acid. This hydrogen's going to go sit next to the lone pair of electrons on the hydrogen and make this H3O+. And so when I'm writing the Kb expressions, I write the base bumping into water and accepting a hydrogen. And this, instead of making the hydronium ion, they make the hydroxide ion. Now we've got these Kb values. So these Kb values are, again, this acetate ion is a really weak base, okay? It's a really weak base. And so, I should get my wording better. The Kb tells me I'm favoring the reactants a lot. And so I'm on this side a lot. And definition of a base is a proton acceptor. A lot of it's not accepting protons, so it's on this side. So same as up here, a low K, this would be the weakest. This ionization would be the weakest, the lowest number. This would be the weakest acid. This would be the weakest base. Okay, so same thing, but applied to base instead of acid. Ammonia would be a stronger base in relative terms. And you'll notice that their numbers, by coincidence, are actually very similar, if not exactly the same, when they're put into two sig figs. And that's a bit of coincidence, FYI. And here's a bit of insight of where we're going. If you times those two numbers by each other, that is to say you do Ka times Kb, but it turns out they equal a constant, which is on your data sheet, Kw, and it equals 1 times 10 to the negative 14. Now, there's a whole topic about, this is all spawned from inquiry question 2, where we talk about the self-ionization of water, in that the self-ionization of water, basically two waters have enough energy to bump into each other and split and make the hydronium ion. Actually, I could do that really quickly now. May as well just incorporate it while I'm talking about it. So two waters can bump into each other, and they just have enough energy. This is an endothermic reaction. At 25 degrees, there's just enough energy to make a small amount of this. And if you go measure their concentrations at 25 degrees, you get 1 times 10 to the negative 7 moles per liter and 1 times 10 to the negative 7 moles per liter. And those numbers are really ugly, so we normally take, we put them into a log form, which makes it a 10 base form. So if I take the negative log of this 1 times 10 to the negative 7, it turns it into a clean number like 7. And this is pH. This is P means negative log. P negative log. And note that by definition, or kind of what neutral means. So I'm now trying to talk about pH equals 7 and what that means, neutral water. So neutral means that they have the concentration of hydroxide equals the concentration of OH. Okay, so it's the only time that they're even, that's neutral. And if you times both those numbers by each other, 1 times 10 to the negative 7, 1 times 10 to the negative 7, you get 1 times 10 to the negative 14. Turns out, if you times the two conjugates by each other, I might use that word a bit. Conjugates are like these two. So these two are conjugates to each other because they differ by hydrogen. Everything, if they're the same chemical formula and they're different by a hydrogen, then they're conjugates. Even OH and water are conjugates of each other. They differ by a hydrogen. You have to get the charge right, FYI. And so what we've got is if we times Ka times Kb, we actually get Kw. And Kw, if we go back to the green formula, if you write out the equilibrium expression like this one, but I now denote it Kw, we do products over reactants. We got our products. And then I don't include my reactant because it's liquid water. And that's a constant. Turns out, if you write out the Ka and you times it by the Kb of conjugates, the everything cancels and you get this. I might show you that a bit later and just below. And what that means, and the reason why this is interesting, is because the acid and the base kind of work in tandem with each other to stay at constant. So if there's a lot of base, there'll be a little acid, and they kind of, as one goes up, the other goes down by the same proportion, by some proportion to keep it at a constant. Okay. And we can use that to our advantage in a lot of calculations. So that's kind of a quick insight into that, although you're going to get way more on it. You can then take the negative log of everything. P equals negative log. Negative log, technically base 10. We're not talking about natural logs. And so you can pK, pKb, pKw. You might notice that there's some certain log rules that you might notice when you times it, it goes into positive. The negative log of 1 times 10 to negative 14 is 14. And so we can start expressing all these Kas and Kbs in cleaner numbers in log form. And we can get out, we don't ever have to write 1 times 4.8 times 3 times 10 to the negative 8. We can just write it as a cleaner number, so whatever that is. So it's a bit of an extra process, but after a while it kind of is better to be in log form than to not. Right. You've learned before about acids and base, metal carbonates plus acids. It goes to salt plus water plus carbon dioxide. You've also learned neutralization reactions are, acid plus base goes to salt plus water. I want to just put it to you, and I don't think it's going to click right this second. This one will require tad thinking. Neutralization, I've said this in previous videos. I want to put it to you that in both those reactions, this is the only thing that's happening. So this is metal carbonate plus acid and acid plus base. This is the real reaction that's happening. And that's why you get the water. Okay, so when sodium carbonate, which is a weak base, by the way, I'm trying to explain why it's a weak base, even though there's a strong arrow. Sodium carbonate, firstly, when you put it in water, even if that's the water that's with your acid, okay? If you put it in water, it dissolves. When it dissolves, it makes 2 sodium ions, and then it makes 2 hydroxide ions and 1 carbon dioxide. So you would go, all right, by definition, just like lithium hydroxide and sodium hydroxide, that should be a strong acid, a strong base, I should say. However, it's under the category of weak base. And so what actually happens is that carbon dioxide, that bubbling that happens when it dissolves, that effervescence, the fancy word for bubbling, some of that dissolves into aqueous sodium carbon dioxide, and that aqueous carbon dioxide can bump into water and make the carbonic acid molecule. Obviously, that's going to then have its dissociations, even if the Ka is quite low. Some of that will split and make the hydrogen carbonate ion and the hydronium ion, and then that hydrogen carbonate ion can further ionize into the carbonate ion. And this is kind of like the ocean, well, this isn't kind of like, this is the chemistry of the ocean and our blood, FYI. So this is actually really important. But if all I'm trying to get out of you is that the reason why metal carbonates aren't classified as strong base is because they do this CO2, and if that wasn't there, it'd be a strong base. But because it's there, you actually get some acidic. Because you get a acidic equilibrium happening, you get your pH. It doesn't spike up into the high pHs like a strong base would. It kind of goes high, but moderately high instead of really high. So to be very clear, sodium carbonate could be or should be a strong base if there wasn't carbon dioxide. However, there is carbon dioxide, and so it's not a strong base. No one tries to catch you out on that. That's just an FYI. Note, I've talked about ionization. I've basically exclusively talked about acids and bases just putting one chemical in water. However, if we're talking about them reacting, weak acids and bases can fully react. So if I put any weak acid or any weak base, and I had enough, like say, strong acid or strong base present in the solution, then that strong base or strong acid would make the weak acid fully react. So for instance, in the example of the magnesium hydroxide, if I've got already a lot of HCl as an example, a lot of hydronium ion already present, the hydronium ion would react with the little amount of hydroxide that's dissolved, causing the magnesium hydroxide to dissolve a bit more, which would allow the acid to react with the hydroxide, and so on, until all the magnesium hydroxide is fully reacted, and all that's left in that solution is magnesium ion and water, essentially, because I've neutralized the OH and the acid, hypothetically. That's also true for any weak acid, so the second ionization of the sulfuric acid ion, or the hydrogen carbonic acid or phosphoric acid. All of those would fully react with a strong base. So if I had a lot of sodium, I should just write that as H2SO4 in purple. So if I have a lot of base present, hydroxide, they would fully react. So just because they don't ionize or split apart doesn't mean they fully react. So a lot of questions in the HSC try to test that understanding, because a lot of kids recognize that things are weak and strong, but they don't accept the fact that a weak acid can fully react. So weak acid partially ionizes, but can fully react if it's in the right circumstances. All right, I might just pause there. The next one's going to be a bit more complicated.